As we all know, SDXL allows to implement the kernel function both in C, C++, or using OpenCL language. Despite the optimizations that we discuss in these classes are applicable to both C, C++, and OpenCL kernels, for clarity during the course, most of the considered examples and directives used to apply the optimizations are shown for C, C++ kernels. People interested in the corresponding OpenCL versions of the optimization can refer to the SDXL optimization guide and to the SDXL programmer's guide, available online on the Xilinx website and on our platform. SDXL leverages on Vivado HLS for performing the high-level synthesis from C, C++, or OpenCL to the actual hardware specification in Verilog or VHDL. Hence, most of the optimization that relates to the implementation of the kernel itself as well as the definition of its interfaces are specified by means of Vivado HLS directives. Alright, so let's consider a very simple C function that we wish to accelerate on a target FPGA. This C function receives as input two single precision floating point vectors and produces as output their sum. For simplicity, we assume that the length of the vectors is fixed to n equal to 1000-2004 elements. Our goal is to implement the function as an SDXL kernel. In order to do so, we need to define the interfaces that the kernel will expose to the rest of the system. While Vivado HLS allows to define different types of interfaces, SDXL has specific interface requirements. Indeed, once the proper interfaces are defined, SDXL will automatically generate the FPGA design and connect the kernel module to the X interconnects of the shell. The kernel interfaces can be defined by means of specials. In general, for each pointer argument, such as A, B, and res, we define a pair master XC and XC Lite interfaces. The XC Lite interface is used to specify the offset at which the data resides in the onboard DDR memory, and is configured during the kernel initialization. The XC master interface, instead, is the actual interface used by the kernel to transfer data to and from the DDR memory. Notice that it is also possible to define interfaces for scalar argument, such as a simple integer argument. In this case, a single XC Lite interface suffices. The value of the scalar will be set on kernel initialization before the actual execution of the kernel. In addition to the argument interfaces, it is also necessary to specify an XC Lite interface associated to the function return, which is needed in order to define the proper signals to control the status of the kernel. For each HLS interface pragma, it is possible to associate a bundle name. All the interfaces associated to the same bundle are grouped to the same XC interface port. Notice that SDXL requires a single XC Lite interface port. Hence, all the XC Lite pragma should refer to the same bundle that we name control. On the other hand, it is possible to define multiple XC master interface ports. We will return to this aspect shortly. For now, we define a single GMEM0 XC master interface port, which is shared for all the three function arguments. Notice, however, that all the argument types grouped onto the same XC master interface port should have the same bit size. In our example, all the base types are float and hence they all require the same number of bits, which is 32. For this example, we target an alpha data at 200 MHz. If we run the high-level synthesis with Vivado HLS, we can get a first estimation of the resources requirement and the number of cycles needed by each execution of our kernel function. Here, it is important to notice that the overall latency of the kernel is dominated by the summation loop. In particular, each iteration of the loop requires 23 cycles, and the loop runs 1024 iterations as expected. Vivado HLS also allows to visualize the scheduling of the operation within the kernel. The span of the yellow line represents the number of cycles needed by each iteration of the loop, while the blue bar below corresponds to the span of the different operations involved within the loop. Here, it is important to notice that in every iteration of the loop, two read requests, one write request, and the corresponding response are performed every cycle. In addition to this, each read and write operation might stall the computation since it needs to wait for the memory controller to complete the corresponding operation. Such stalls might severely impact on performance, especially because they are encountered at every loop iteration. The main culprit for this initial naive design is the fact that we read very few bytes per each memory transaction. Here we are moving one float at a time, which is 4 bytes. Note also that 4 bytes is the minimum amount of data that SDXL allows to request per memory transaction. In the following classes, we are going to explore different optimizations we can apply to our context to achieve better results.